Reducing the price of anarchy. As we have seen, the price of anarchy can be large in both non-atomic and atomic selfish routing games when cost functions are highly nonlinear. This motivates a question first posed in section 70.3. How can we decide or modify a selfish routing network without explicitly imposing an optimal solution to minimize the inefficiency of its equilibrium? Can modest intervention significantly reduce the price of anarchy? We briefly discussed two techniques for mitigating the inefficiency of selfish routing in non-atomic instances: influencing traffic with edge taxes, subsection 18.5.1, and increasing the capacity of the network, subsection 18.5.2. Marginal cost sharing, our first approach to reducing the price of anarchy in non-atomic selfish routing games, is to use marginal cost taxes on the edges of the network. The idea of marginal cost pricing is to charge each network user on each edge for the additional cost its presence causes for the other users of the edge. To discuss this idea formally, we allow each edge E of a non-atomic selfish routing network to possess a non-negative tax pi E. We denote a non-atomic instance GRC with edge taxes pi by GRC plus pi. An equilibrium flow for such an instance GRC plus pi is defined as, in definition 18.1, with all traffic traveling on routes that minimize the sum of the edge costs and the edge taxes. Equivalently, it is an equilibrium flow for the non-atomic instance GRC to the pi, where the cost function CE to the pi is a shifted version of the original cost function CE, such that CE to the pi of x is equals to CE of x plus pi e for all x which are greater than equals to 0. The principle of marginal cost pricing asserts that for a flow f feasible for a non-atomic instance GRC, the tax pi e assigned to the edge e should be pi e equals to fe times ce prime of fe, where ce prime denotes the derivative of ce. Assume for simplicity that the cost functions are differentiable. The term ce prime of fe corresponds to the marginal increase in cost by one user of the edge, and the term fe is the amount of traffic that suffers from this increase. We can also interpret the marginal cost text pi e using corollary 18.10. Pi is precisely the extra term in the marginal cost function that is absent from the original cost function. These taxes correct for the failure of selfish users to account for the second altruistic term of the marginal cost function. Formally, corollary 18.10 easily implies the following guarantee. Theorem 18.27. Let GRC be a non-atomic instance such that for every edge E, the function x times c of x is convex and continuously differentiable. Let f star be an optimal flow for GRC, and let pi equals to fe star times c prime of fe star denote the marginal cost text for edge E with respect to f star. Then f star is an equilibrium flow for GRC plus pi. Marginal cost taxes thus induce an optimal flow as an equilibrium flow. In this sense, such taxes reduce the price of anarchy to 1. Theorem 18.27 also holds with weaker assumptions on the cost functions. In particular, the convexity hypothesis is not needed. For further discussion of pricing problems in routing games, see Chapter 22. Capacity augmentation. Our final result is a novel type of bound on the inefficiency of equilibrium flows in non-atomic selfish routing games with arbitrary cost functions. This bound does not involve the price of anarchy, which is unbounded in such networks, example 18.3, and instead shows that the cost of an equilibrium flow is at most that of an optimal flow that is forced to route twice as much traffic between each source sink pair. As we will see, this result implies that in lieu of a centralized control, the inefficiency of selfish routing can be offset by a moderate increase in link speed. Example 18.28. Consider the nonlinear variant of P-Gauss example 18.3, when there is one unit of traffic. The equilibrium flow routes all of the flow on the lower edge, while the optimum flow routes epsilon units of flow on the upper edge and the rest on the lower edge. When epsilon is approaches zero as p goes to infinity, when the amount r of traffic to be routed exceeds 1, an optimal flow assigns the additional r minus 1 units of traffic to the upper link, incurring a cost that tends to r minus 1 as p goes to infinity. In particular, for every p, an optimal flow feasible for twice the original traffic amount r equals to 2 has cost at least 1, the cost of the equilibrium flow in the original instance. We now show that the upper bound stated in example 18.28 for the nonlinear variant of P-Gauss example holds in every non-atomic instance. Theorem 18.29: if F is an equilibrium flow for GRC and F star is feasible for G2RC, then C of F, which is less than or equals to C of F star. So, proof. Let F and F star denote an equilibrium flow for GRC and a feasible flow for G2RC, respectively. For each commodity I, let DI denote the minimal cost of an SITI path with respect to the flow F. Definition 18.1 and the definition of cost 18.1 imply that C of F is equals to sigma of index I of the term Ri times di. The key idea is to define a set of cost functions, C bar, that satisfies two properties: lower bounding the cost of F star relatively to that of F is easy with respect to C bar, and the new cost functions C bar approximate the original ones C. Specifically, we set CE bar of X is equals to the maxima taken among the term either C of FE or C of X for each edge E, and let capital C bar dot denote the cost of a flow in the instance GRC bar. Denote that capital C bar of F star is greater than or equals to C capital C of F star, while capital C bar of F is equals to C of F. And we first upper bound the amount by which the new cost, capital C bar of F star, can exceed its original cost C of F star for every edge E. CE bar of X minus CE of X is 0 for X which is greater than or equals to FE, and bounded above by CE of FE for X which is less than FE. So that means X of CE bar of X minus CE of X, which is less than or equals to CE of FE times FE for all X which is greater than or equals to 0. Thus, capital C bar of F star minus C of F star is equals to sigma, summing for all edges little e in capital E of the term FE star times CE bar of FE star minus CE of FE star, which is less than or equals to, again, sigma for all edges of the term CE of FE times FE, which is equals to capital C of F. And in other words, evaluating F star with cost functions C bar rather than C increases its cost by at most an additive C of F factor. Now we lower bound capital C bar of F star. By construction, the modified cost CE bar dot of an edge E is always at least C of FE, so the modified cost CP bar dot of a path P in Pi is always at least Cp of f, which in turn is at least di. The modified cost C bar of f star therefore equals sigma summing for all P in fancy P of the term Cp bar of f star times fp star, which is greater than equals to doubling summation, where outer summation summing for all index I starting from 1 to k, into the inner summation summing for all P in Pi of the term di times fp star, which is equals to, if we merge the doubling summation, the term instead of that, and just leave the outside of the summations of index I starting from 1 to k, which is equals to 2 times ri times di. That is, that equals to, if we take out a constant, there will be 2 times c of f. So the theorem now follows immediately from equations 18.10 and 18.11. Another interpretation of theorem 18.29 is that the benefit of centralized control is equaled or exceeded by the benefit of a sufficient improvement in link technology. Corollary 18.30 let GRC be a non-atomic instance and define the modified cost function CE wave by CE wave of x equals to CE of x divided by 2, then divided by 2 for each HE. Let F wave be an equilibrium flow for GRC wave with cost capital C wave of F wave and F star a feasible flow for GRC with cost C of F star, then capital C wave of F wave is less than equals to C of F star, and simple calculations show that theorem 18.29 and corollary 18.30 are equivalent. See exercise 18.8a. Corollary 18.30 takes on a particularly nice form in instances in which all cost functions are mm1 delay functions. Such a cost function has the form c of x equals to ue minus x, then to the inverse, where ue can be interpreted as an edge capacity or a Q service rate. The function is defined to be positive infinity when x is greater than or equals to ue, rigorously allowing infinite cost. In this selfish routing model requires some care. We ignore these issues in this chapter. In this case, the modified function CE wave of corollary 18.30 is CE wave of x, which is equals to 1 divided by 2 times ue minus x over 2, which is equals to 1 divided by 2 times ue then minus x. Both of the 2 ue minus x is in the denominator. Corollary 18.30 thus suggests the following design principle for selfish routing networks with MM1 delay functions. To outperform optimal routing, just double the capacity of every edge.